kill the value after a while. Some of the simulation results, this is without the fault for the first state and second state. And follower 1 without the fault. The more interesting would be the things with the fault. We introduce the fault like this with at the 5 seconds, so this is the time description of the fault. The parameters of the neural network require tuning, so this is based on kind of try and error or little experience, as well as the size of the network. 30 hidden nodes is, in this case, reasonably powerful network. It can go more, probably not too much less. Now with the fault, you'll see there is a peak in the error here and the norm of the error, and also for another state, a peak of the error, indicating that something happened. There is a fault there. This is a neural network weights, basically just to show that they're bounded and that the system does not go unstable. The follower 1 also can detect the problem, but as that experiments show, even after 1 hop, it's affected less and less. So if I'm emotionally disturbed, then I will probably disturb my child a little bit today when I come home, and then my child maybe be a little also stressed out, disturb the friend, and that will die down after 1 or 2 hops. So those are some of the coefficients, coupling factors, and their estimates. So we think, and this is ongoing research, that we can use system theory for modeling of the emotions. We develop a neural network-based estimator mostly for electromechanical systems, but the next step we'll see how we do this for social groups. Theoretical results we developed with the put-up theory. Now this was interesting for me. We then started working with a professor from psychology, basically NSF officer told us that this is really cool idea, they liked it very much, but they say, we just want your experimental data, and then we'll talk about it. So we partnered with a professor from psychology, and we hired a computer science student. So we started developing, this is like first maybe beta version, we developed application on the Facebook, where students will grade the happiness level and anxiety level twice per day as a part of the large psychology course. They will choose the friends and link the friends on a limited basis to really form like quote-unquote sensor network. Not every node is connected to everyone. I have 3-4 close friends. Those friends are, and then I will also establish what are my weighting factors of the link. I may be close with one friend, but maybe not to all of them. And then the measure basically get the data of what happens when there is a drama in somebody's life, how that affects the next person and the next person. And to see, maybe we won't get anywhere, but we're quite excited with this to combine some of the electrical engineering and systems theory to something totally unrelated in psychology. And the latest thing I wanted to talk about, this nice and new lab that we developed with the Python system opened some completely new opportunity that we didn't think about. So we want to use gesture-based sensing and control for sensing and control. We want to detect gestures, something like for you guys that have this Kinect Microsoft system. Kinect can detect motion of hands, but on a global scale, cannot detect finger movements because the camera is not that sensitive yet, and you can detect just if there is the movement of the whole body, basically. The icon system allows us to detect finger movements on a millimeter level. So that's the advantage. Now, you might ask yourself, one of these cameras costs $10,000, so 10 cameras, 100,000 with the software that's close to 180,000. Who will buy $180,000 system in the house? But for research, you need to understand that maybe 5 years from now, every computer will have 3 little cameras when you open the laptop. 5 years ago, laptops did not have a web camera built in. You needed to buy a camera, bulky camera, install the driver, maybe still don't work. So this gives us advantage to try something that in the future might be used in different areas, in the gaming industry or some others. So we developed a glove with multiple markers that can be seen in 3D. These markers, we are still debating where to put them. There are many things now. This is just by itself is a research how it's a trade-off how many markers you want on your hand, where to position them. The more you have it, you have better accuracy, but it takes more to process. And so those are some challenges. To develop appropriate model, to develop good classifiers. It's really a classification problem. Right now we put some neural network classifier, but we are still not 100% satisfied with the performance. And we can detect only few gestures. Stop sign, 1.1 finger, 0.2 finger, fist, and one more. So 4 or 5 gestures we can detect. But even that is enough for something that we envision in the future how robots will be controlled. Both NASA and Air Force expressed the interest for this. Air Force for the reason that they say in the battlefield, and I fly with my son this little airplane. It's very difficult. It requires complete focus to fly the plane. If you ever done that, it completely occupies your brain. Now, Air Force says you're under fire, you're in the battlefield, you're dodging everywhere, bombs. You can't fly now focusing and flying your plane. You can't do that. So you need a simplified interface. But what's simpler than trying to fly it by hand? You kind of fly like this. That would be pretty cool. So what we now have with only these 2 signs, we want to have the robot called like human. We want to do this, the robot comes towards us. We want to say stop, robot stops. We want to say point finger, robot goes in that direction. We say stop, robot stops. So I think it will, what makes iPhone revolutionary, it's not maybe microprocessor or fancy screen. iPhone is revolutionary because of the fantastic user interface in 2D. You zoom in, something like this, you swipe this, there's another application, you swipe like that. We envision, not only us, there is other people in groups, that in the future there will be 3D interfaces, that I will not need to press the button here to make your slide going, that I will maybe just wave the hand to see another slide, that I will point the finger without this thing, you will see what I'm trying to say. So that's where we are excited about this gesture-based computing and control. We made the software, we submitted a patent on this, but there are still ways to go to achieve this. So with this, I would close the talk. If you have any questions, I gave a little overview of where we are going and what we achieved. And if you have any questions, I would be glad to try to answer. Yes?
You showed a bunch of robots trying to detect an electromagnetic source, and used a bunch of robots to find the source because they had directional antennas. I think if you had one robot with an omnidirectional antenna, you could use the Doppler effect to get the direction and the RSSI to get magnitude. So you could potentially find an electromagnetic source using just Doppler and
So
RSSI.
really, so the first part I would agree with you, and actually that's what we have. We have multiple static ones, but really right now we are flying only one in the zigzag pattern.
Okay.
So one is mobile. But we didn't think about the second part, what we said. It's a pretty cool idea. We do have a Doppler radar for basically detection of movement for like a smart fence system, but we didn't think about this, what you said.
So I mean, if the robot is moving towards the source, the frequency shifts, and
Yes.
away from the source, it shifts the other way. You could use a phase lock loop to essentially servo to a constant radius.
Yeah. Yeah, that's pretty cool. We might try that.
Yeah, any other questions?